Okay, let's move to the example 4. Another example related to the non-reactive. If the enthalpy or specific enthalpy is not available in the reference table, 100 gram moles per hour of liquid and hexane. So we have start with the extract all the information given here. So we have N1 is at gram mole per hour in liquid. So in liquid at 25 degrees Celsius and 7 bar is vaporized. So the system is a heater. So okay, the second state is vaporized. That means it turns to the vapor to 300 and constant pressure. So we have 7 bar. Neglect the effect on of pressure on the enthalpy, estimate rate at which heat. Okay, so we need to determine the rate of heat. So this is our first step. The second step is to perform the balance. So we have Q. The general balance is minus shaft work equal to delta enthalpy plus delta kinetic energy plus delta potential energy. So we may perform assumptions to simplify this equation, and in order for us to solve the problem, so we have this, okay, since this is involved only heater, there is no moving part observed here, so we may neglect the shaft work, and then the potential and kinetic also can be neglected. So the Q or rate of heat here equals to delta H. So delta H equal to output Ni Hi minus input Ni Hi or specific enthalpy. So we start with this. The third is form and hexane. From the liquid 25 7 bar to vapor 300 7 bar. So the first thing is to check the boiling point at table B1. What is the boiling point of the N-hexane? Because from the liquid to vapor, we may need to find the boiling point before we can move from the boiling point to the desired output temperature here. So you can perform the path. Okay, finding the boiling point is at 69 degrees Celsius and 7 bar. So after that, we can change this to vapor first. So that means from the liquid to vapor, we have the liquid vapor at 7 bar. And then after that, we can move from the 69 to 300. So we have three paths to be calculated here. So we have this maybe A, and then this is our delta B, and this is our delta C. So the fourth here, fourth step is to determine the each path here. So H here equal to V, because we only have the different temperature. So for the different temperature from 26 to 69, Cp in liquid dt plus, okay, for delta Hb here, we have the change of the phases here. So for the vaporization plus, and then the third is temperature plus 69 to 300 and Cp in vapor dt. So the answer is, I just share the answer with you. So for the first, we have A here we have 9.44 kilojoule per mole. And then for delta HA, okay, delta HB or delta H at vaporization, this is, you may also refer to table B1. So you can get this 28.85 kilojoule per kg, and delta HC equal to 7.1 kilojoule per mole. So we have this, okay, Q equal to delta H equal to N, because we have 2 unit here, mole per hour times delta H kilojoule per mole. So by changing the unit from this, we can get equal to 85.5 kilojoule per mole, per mole here equal to, okay, to convert it, we have 100 mole, this is per hour, and then 3000 second per hour. So we have 1 kilojoule second per 1 kilowatt. So the answer is 2.838 watt kilowatt. So this is your final answer for this question. So all the data for CP at the liquid and vapor, you may refer it. I can write here table, from table, reference table in your, okay, maybe I can share to you the table here. Table B1. First okay, for table B1 is the detailed information about the boiling point and also the vapor heat at vaporization. And we can refer to table B2 for CP. Your n-heat scene. If you can see here, we have this. You may refer to this for the n-heat scene. How to solve this, and then you can try it by your own